Now that we've defined partial derivatives, let's have a look at a few examples, and you can also find them in section 8.2 of your lecture notes. In this example, we want to find all the partial derivatives of this function. In this case, it depends on two variables, therefore we need to calculate f of x and f of y. With the notation that we've used, this partial derivative in respect to x is df dx. In this case, when we look at the function, we see that this term does not depend on x, therefore this will be 0. This will also be 0 because it's a term that's adding, it's not multiplying. And the only thing you're differentiating is this, which ends up being 4 times x to the power of 3. Therefore, the partial derivative in respect to x is very simple. You could write this if it's your first time doing partial derivatives. They're just 0 because they do not depend on what you're differentiating against. For y, we calculate df dy, and now this has no dependence on y. Same thing with 10. The only thing we're differentiating is 6 square root of y. 6 square root of y is the same as 6y to the power of 1.5. We can use the exponent rule. We drop it, this becomes 3y minus 1.5. It's the same as 3 over square root of y. And that's it. In this simple example, calculating all the partial derivatives are just about calculating the one with respect to x and y. Let's have a look at the next example. In this example, we have a function that is slightly more complicated, but we can still proceed in a similar way. First of all, let's calculate the partial derivative in respect to x. That's df dx. And whenever we want to calculate this, everything that does not contain an x is a constant. In this case, we can identify that there's an x here and also an x here. We can see that we'll have to use the product rule and also chain rule for both cos and e to the power of x squared. We can start with these terms first. So we'll have the derivative of this part times this function and the derivative of this part of the function. We can start by differentiating this function that we could call f of g of x. This will be, we get the derivative of the inside because this is a composite function, that is minus 4 over x squared times the derivative of cos of u. That's going to be minus sine of 4 over x, and this will be multiplied by e to the power of x squared y minus 5 y cubed. And this will be plus, and now we're keeping cos of 4 over x, and we're multiplying by the derivative of this function, which is also a composite function, and therefore we need to multiply by 2xy. Remember, in this case, y becomes a constant. We're differentiating against x, and multiplied by e to the power of x squared y minus 5y cubed. Once you get to this stage, it's a very good idea to take the e to the power of x squared y minus 5y to the power of 3 and bring all the other terms together, which I'll just do here. And all I did really was take the factor e to the power of all this from both these terms, recognizing this, of course, being multiplied, and minus gives you plus. In this case, there's just two terms. This would be your final answer for the partial derivatives in respect to x. In respect to y, we need to clear the board so we have space. That's better. We can finally calculate the derivative, partial derivative of f in respect to y. That's the same as df dy. This one is just slightly easier because this is now a constant, so you're just differentiating this function. And differentiating this function is chain rule. It's the derivative of this part times the function itself. The derivative here will be x squared minus 15 y to the power of 2 times e to the power of x squared y minus 5 y to the power of 3. And this would be our final answer. The partial derivative in respect to y is much simpler than in x because only the exponential depends on y. I hope that this is now relatively clear. In the lecture notes you'll find even more examples. I'd also encourage you to try them, and if you have questions, just get in touch, preferentially via Teams, but also if you prefer, just drop me an email.